All right. Welcome to the Quantum Internet Research Group. We'll start in about 1 minute here, I hope. Let's see. Share slides. Confirm my selection. There we go. No reply from Edeco yet. They're tinkering with that one. Let's see. Where do I see the participants list? How many people are here? What? There we go. Off to that side there. All right. Give us, let's see. Well, maybe we should go ahead and start. Could you reply to them about the camera? Yeah. All right, so welcome to the Quantum Internet Research Group, and we have what I think is an interesting agenda today. I am one of the co-chairs, Rodney Van Meter. Our other co-chair is online, Wojtek. Wojtek, say hi.
Hello.
And
Can you hear me?
also,
Yeah, okay,
yes, we can hear you. Good, thank you. And we also have with us today Suzanne Wolf, who's helping me to run things up here on stage. So let's see. As you all know, this is the Quantum Internet Research Group, which is a research group of the Internet Research Task Force. And this session is being recorded. We have the usual note well. Get rid of that so I can see this a little better. The IRTF follows IETF intellectual property rights and things of that nature. By Wednesday afternoon, most of you should be familiar with this. Please check the text if you are not. And also, as I just noted, this session is being recorded, both audio and video recordings. So if you are here, you are participating in the usual way. And if you step to the mic or turn on your camera, then you are giving permission to be recorded. Also, the usual issues of privacy and code of conduct. We do expect everyone to be polite to everyone else in the room and follow the expected IRTF, IETF code of conduct. If you have any problems or any concerns with somebody not being sort of supportive and helpful in some way, shape, or form, come see me or Colin Perkins is the IRTF chair, or the ombudsman if you're not comfortable approaching either of us. So the goals of the IRTF, as always, the Internet Research Task Force focuses on longer-term research issues rather than building protocols toward standards. The IRTF is not a standards research organization. So the outcome of the work you will hear about today is not necessarily an RFC, and hopefully it will be useful to you in some long-term or some positive way after that. see. As we've noted already, meeting tips, the session is being recorded. Please make sure that you sign in using the QR code that's on the screen or directly through the agenda online. Keep your audio and video off if you are either in the room or remote, because if you're in the room, it causes problems. And if you're remote, you wind up showing up on the screen where everybody else can see you. So the tools, just in case you need them, the on-site tool is available from the agenda. It's the little green telephone. The chat room, which is in Zulip, is the other green icon. Those two things are not necessarily as obvious as they might be in the icons change from meeting to meeting. If you're using the online tool, you'll see the screen as in the upper right. If you're using it on your cell phone, you'll see it as in the screen on the lower right. And if you need to ask, if you want to ask a question, please join the queue by raising your hand using one of these tools, regardless of whether you're online or in person, so that we can manage them as one queue. So let's see. Agenda for today. We have 1, 2, 3, 4 good talks plus some additional room for additional business. The agenda for today is a little loose, although we've managed to consume a couple of those minutes already. So I'm going to give people a little extra time if necessary in the sessions in the talks as we go. The first item on the agenda is routing and quantum networks. I heard the speaker, Michael Kubedu, give a talk a few weeks ago, and it was fantastic. So I'm looking forward to the longer version of it he's going to be giving us today. Second will be timing regimes for quantum networks, which is a document that's in progress but not yet public, that's being developed in our own research group. Excuse me. And then Diego Lopez will give us an update on his internet draft. And then finally, there will be a talk on link level multiplexing given also by a member of our group. That's the proposed order and agenda, but I don't actually see our first speaker online. So I'm
here. Can you hear me all right?
Ah, good. Yes, I can now hear you, but I don't see you in the list of participants for some reason or another. Maybe your name's not entered into the system right. Good.
My alias is invited speaker 1, so that's probably.
Okay. Maybe let's see. Do I see invited speaker 1? When you turn on your camera, you will pop to the front of my list, and so I'll be able to see you a little better there. Good. Yes, I see you now as invited speaker number 1. All right. Let's see. I think there's one more slide here before we go. Document status. Just 1 or 2 more administrative things before we go on. The application scenarios for the quantum internet has been sent to the RFC editor, and so that will be published as an RFC after the usual editing procedure is done. It was sent to the RFC editor in December, so it's making its way through the queue now. And the -01 draft of Diego Lopez's a multiplane architecture proposal for the quantum internet. The 01 draft was submitted on March 4th, and so Diego will be talking about that shortly. And finally, I'm going to abuse my chair privileges here and just put in one plug for one thing that's coming up. In September, there will be the workshop for quantum repeaters and networks. This will be the 4th workshop in this series, and it will be in beautiful Montreux, Switzerland. And participation is by application. You have to write a couple of paragraphs saying why you want to come join us to talk about quantum networks. And we could very much use the participation of people from this community. And with that, let's see, that's it. Nigel Davis asked to share slides. Nigel Davis entered the queue. Who is Nigel Davis? I will stop sharing the slides here. Let me share the quantum routing slides. Confirm my choice here. Let's see. Yep. Now, how do I give him the control here?
I hit the Ask Slides button.
Sorry, say that again.
I hit the Ask Slides button maybe you should see a request on your end.
Where do I see that? Aha. Portakana. I'm new at driving. Excuse me here. What do I see here? Grant pre-loading slides. There we go.
Great.
All right, Michael, you should now have control over that, I think. You're up.
Yes, I do. All right. Great. So thank you for the introduction and the invitation to speak to all of you today. It's a great honor to be here speaking to the QIRG. So I gave this talk at APS March meeting a couple weeks ago when Rod was there and invited me to give a talk to this group. And today I'll be talking about routing in quantum networks. This is some research and a survey paper that I've been working on with some colleagues at NIST. My co-authors are Amar Abane and Vansi Mai. The paper is not yet published on the archive, but will be in the coming weeks. So I will communicate with Rod to send him the link once it's published. But this should give you a pretty good idea of the scope of the paper. All right. So just to ground ourselves in the scope a little more. So the purpose of this paper was to survey literature published since 2017 on entanglement routing in quantum networks. We considered papers that focused on first generation quantum repeaters and quantum routers. So we are not in the regime of full fault tolerance by any means. We considered entanglement routing for bipartite entanglement, so not dealing with high dimensional cluster states or anything like that, so just two-party entanglement. The motivation for this was really to provide a unified terminology for some of the concepts in entanglement routing, while also making this problem more accessible to network engineers who may be coming from more of a classical networking background. And we do this by drawing analogs to some routing concepts from classical networks. In terms of the protocols that we assume these networks support, we have heralded entanglement generation, entanglement swapping, entanglement purification, and teleportation. So we're assuming these networks can support those protocols. And here's an example architecture on the left of a simplified first generation quantum repeater. So we have some memories, we have the ability to do Bell state analysis, we have hardware control, we have the ability to do some quantum operations, so gates for doing things like purification circuits or teleportation corrections. So that gives you a sense of the functionality of the repeaters and the routers that we considered in this paper. Okay, so continuing with the theme of drawing analogs to classical networks, we can begin to map some of the quantum network functions to different layers in a stack. This is by no means a standard, but generally, as we were surveying literature, we were able to kind of map these functions to different layers, somewhat analogously to the OSI model in classical networks. These different quantum network functions have different scopes, both at the physical layer, link layer, all the way up to network and transport, but they also are associated with different timescales. And so this figure kind of captures, okay, what are the supporting classical communication technologies that we need to enable these protocols? What are the classical processing functions to support these protocols, and how are they implemented? So for example, at the physical layer, we're dealing with time tagging, coincidence detection, stabilization. These things need to have picosecond or nanosecond resolution. So implementing such protocols with classical technologies would require FPGA or ASIC. As we move up and up the stack, we can think about network level protocols. So for swapping strategies, routing lookups, path recovery, functions like that. These can be implemented in a microcontroller, some kind of network operating system, or SDN controller. These don't have as stringent timing requirements as some of the lower layer protocols. Okay, so let's get into the problem formalism for quantum routing. Again, this is not a standard, nor is it consistent across all of the papers that we surveyed, but generally, the routing problem formalism can be described. We have some networks, some set of nodes and edges, and the idea is that the network receives a set of requests from user pairs, and so users will define a request as such, where they specify the nodes receiving the end-to-end entanglement. They may also specify a delta here, so that's the desired entanglement generation rate. They also may specify some kind of minimum fidelity threshold. And the reason for that is that certain applications may require a certain level of entanglement fidelity for the application to be successful. And not all papers considered this notion of fidelity as part of the request itself, but it was our opinion as authors to include this as part of the formalism as we studied how routing and path computation is actually quite coupled to quantum entanglement fidelity. Okay, some key parameters here shown on the right. So quantum networks are inherently probabilistic and stochastic, and this is really what differs from classical network technologies. So we have probabilities everywhere. So we have PUV here, and this is the probability of generating elementary entanglement on a channel between nodes U and V. Okay, and this probability must take into account the photon source and detector efficiencies, the channel parameters. So what's the attenuation? What's the link distance? How many attempts per time slot can we do on this channel? So all of these factors inform what this PUV will be, and we begin to consider link metrics and comparisons of paths from this. Then we have PS, the probability of a successful swap. So each router here has a certain probability of actually doing the swapping operation successfully. If these routers are implementing their swapping operations with linear optics, then this is upper bounded by 0.5, but other implementations may go beyond this. But generally, this is what we expect for swapping success probability. Then finally, we have the notion of edge capacity, similar to bandwidth in classical networking. And the idea here is that the edge capacity between U and V is defined as the maximum number of entanglements that can be generated in a single time slot between nodes U and V. So this will need to take into account the different multiplexing modes that may be employed if we're using time multiplexing, spatial multiplexing, or wavelength multiplexing. This all informs the edge width or edge capacity. It will also take into account the qubit capabilities at the end nodes U and V, right? How many memory interfaces do they have? How many entanglements can be stored simultaneously? And this will inform us, how many paths can we actually allocate to a certain link. Okay, so now that we've defined some of the key parameters and the notion of requests, we can talk about the objective of quantum routing. So we want to maximize some notion of aggregate utility here. So on the figure on the right, you can see some different requests coming in between S1 and T1. That's the blue path. Also, other requests for S2 and T2, and we can have multiple requests for that link. And as you can see here, the orange and the red paths differ, but they still reach the same end nodes. So we have these requests, and we want to maximize the total number of end-to-end entanglements delivered for all requests. So we want to satisfy all of them if possible. A small caveat here is that these objective functions are not standard or consistent across the papers that we surveyed. So one can make this more nuanced, and the objective function may take into account notions of fidelity support or some sort of weighted maximization if there was some priority allocated to certain user pairs or requests. Okay, so what is the output of quantum routing? Well, it's a set of paths. It's a set of schedules and instructions for installing these paths and the relevant instructions down to the routers themselves. Okay, so this may be hard to read on your end, but I'll zoom in a second here. What we did is we provided a proposed taxonomy or categorization of different routing strategies that we surveyed. So we kind of broke up the quantum routing problem into two branches here. So the first is routing, and routing is dealing with paths. So path computation. How are these paths computed? Which entities in the network are in charge of computing these paths? And now we can see some analogs to classical routing techniques. So there are distributed ways of doing this, and there's some centralized SDN way. So somewhat analogous to the different ways of doing OSPF and BGP in classical routing. Then there's route installation, and we can consider static routes and dynamic routes. So the idea of static routes is that your network is hard-coded. It's pre-configured to support hard-coded paths, whereas dynamic routes, we are sort of reacting to network availability, network resources. We're reacting to the requests, and we can decide on the paths from there. We also considered a suite of optimization algorithms for computing such paths. So we looked at path search on graphs, Dijkstra's invariants, linear programs, AI-based optimization, and we did a complexity analysis of the different categories of optimization algorithms. The other branch of the routing problem is what we call forwarding. So this deals with, how does the quantum information actually move around? How is it processed? And what are the behaviors that the routers themselves will enact? So what protocols are they enacting on these states? So we have the notion of fidelity support. If a request requires a certain minimum fidelity, we can do this passively by allocating better hardware or more resources to that request, or we can do something more active using tools like purification or small-scale quantum error correction or error mitigation routines. And there are different schema we can consider for that active fidelity support. Another notion that's very important is path recovery. Things go wrong all the time in quantum networks. Photons get lost, swaps fail. So we need to have the ability to recover from changes in the topology and changes in link up-down status, et cetera. We need to be able to handle these expected and unexpected failures in the network. And then we considered a suite of swapping strategies and different ways to schedule swapping operations across routers in a path. And I'll touch on some of those in more detail in a little bit. Okay, so let's talk about some classes of the route installation that we considered. So proactive routing is the first example. The idea here is that path computation is done before any entanglements are generated. Okay, so the controller that is deciding on the paths and these schedules and instructions, it needs to know the full global physical topology. But this can be done centralized or distributed, like OSPF or BGP. Reactive routing, on the other hand, we are reacting to the virtual topology of the network. Okay, so the network goes and generates entanglement, and every so often it will report the virtual topology or the state of the network or a portion of the network to the controller. And that controller then will do its path computation and continue with swapping to get to our end-to-end path. So the idea is path computation is done not on the physical topology of the network, but rather a virtual one, and we're reacting to the state of the network. This can be more effective for resource management and protocol scheduling, as we're reacting to the real-time state of the network. However, every second we spend doing path computation here, our entanglements are decohering, right? So there's a big latency constraint on this approach. Then there's virtual routing that we considered. So somewhat similar to reactive routing, but we're building this virtual graph where path selection is executed. So these multi-hop links can be combined together to create our end-to-end path. We can decide on these virtual links a priori, or we can just react to them, and they're generated randomly. However, here, each virtual link can only be used once, right? We considered opportunistic routing as well, and the idea for this approach is to kind of build up the path as we go from hop to hop, from one endpoint to the other. So we can make decisions hop by hop and define some rules on what the next hop should be based on local state in the network. I will say that these four categories that I mentioned, they can be combined and actually used together. So some papers considered, for example, marrying the reactive routing with virtual routing. Okay, let's get into the forwarding side of things. So swapping strategies are really interesting to consider here. So what is a path? Under the hood, it's a repeater chain, right? We want to get entanglement from A to E, and there are different ways to do that. Different sequences we can get there. So here are some different schedules that one could install to achieve the same end goal, but they all have different properties. So we considered what's called synchronous swapping approach, where all entanglements are created at the same time and all swaps succeed at the same time. So that's example C there. This has pros and cons. So synchronous, when things go well, awesome, we have very fresh entanglement. All our entanglements are arriving at the same time. We immediately do swapping on all the routers, B, C, and D here. And we get the freshest possible entanglement end to end. So very high fidelity. But everything needs to go right. So the probability of success is much lower than the others. So we need many repetitions to do this. Asynchronous, on the other hand, we assume that all the local entanglements are ready before any swapping begins. And this requires memory. We need to store these entanglements as we're waiting on other entanglements. But the idea is we can decide on a schedule a priori and say, okay, hey, router B, you're going to do your swap first, and then router C, and then router D, etc. The final one we considered is opportunistic, where the repeaters act somewhat independently. This is also sometimes called as soon as possible or greedy swapping. The idea is if I'm a router, if I have my left side entanglement and my right side entanglement, that's all I need. And I don't need to wait on anything else. I can just go ahead and do my swap. And then I'll report the results to my neighbors. So there are other considerations than just swapping, scheduling, and the paths. So we considered, as I mentioned before, the actual algorithms for optimizing this objective function. So we looked at Dijkstra's path search on graphs, greedy algorithms, LPs, and AI-based. So we did a complexity analysis of those. There's some interesting questions that arose in the notion of fidelity support. So passive fidelity support versus active. Do we purify on local links and then swap, or do we swap first and then purify on longer distance links? There's no one size fits all here. It depends on your network and your node capabilities. Also, purification there's no one size fits all there either. So different purification schemes and circuits use different numbers of resources. They consume different numbers of bell pairs, and they require certain computational capabilities at the nodes themselves. And the point here is, the link cost metrics become more complicated as we consider this fidelity support. How do we compare a proposed path A to a proposed path B? What are the right link metrics to consider, and how do we combine those link metrics to compare one path to another path? And then finally, path recovery. This is something that we found somewhat lacking in the literature. A lot of the literature proposed routing strategies considering the happy path when everything is right. But they didn't do a lot of analysis into how do we recover from expected failures, how do we install, for example, our alternate routes or alternate paths. But we need to be able to handle decoherence, photon loss, and the operational errors themselves. And when things go wrong, there are different things we can do, right? Do we regenerate entanglement if it's too old, or do we preserve it with some more active purification or quantum error mitigation routines? Okay, so I'll end with some open questions that we came up with. So this really led us to a lot more work we can do on this, and yeah, I'd love your input and where we should take this next. So, what is the optimal topology for a given network, and what is the optimal use of that topology? The routing schemes for second and third generation repeaters will be quite different than the first generation. So especially third generation repeaters, or what are called one-way repeaters, this becomes a lot more like a classical network. It's a transport network. Your quantum information is flowing, unidirectionally across the path, instead of this first generation where we have this entanglement swapping and kind of stitching together these local entanglements. I think the biggest one for me is this number 3. How coupled should the routing and forwarding be? I think the best routing algorithm should take into account all of this stuff. It should take into account swapping schedules. It should take into account purification. So not just considering the link metrics just based on the entanglement probabilities, but rather all of the protocol scheduling that informs how good a path is in the context of all these other requests. So I think they should be coupled. Some papers did couple them, others did not. But I think that's an interesting open question we can consider. Data plane overhead analysis. So all these protocols come with a certain data plane overhead in terms of communication that's necessary. This adds latency to the whole process. So more kind of complexity analysis into the data plane overhead is another future direction. As I mentioned, failure recovery is something that we found somewhat lacking in literature. So we need to study that more robustly. And then consider more heterogeneous networks. So we have different links and different hardware capabilities. This makes the problem more interesting. Great. So with that, I'll end. Thanks for listening. And yeah, you can reach out to myself or my co-authors here, and stay tuned for the archive publication. I promise it is coming very soon. Thanks again.
Cool. Thanks very much. We're about on time, so if there are questions, comments, we have time for a couple. I see Kariti in the queue. Go ahead.
Hi, thanks for the talk. I do want to plug a draft that we wrote like 5 years ago, which is about advertising properties of entanglement in OSPF or ISIS. So you can do the kind of computations you just talked about. So we talk about, how many communication qubits do you have? How many memory qubits do you have? What distillation, or you call it purification strategies, you can support on the node. So when you create, you can then, as you said, create these different paths. And when the path, is complete, then you might want to do your the purification, or as you said, you might want to do the purification on a hop-by-hop basis. So that thing has been sitting dormant for a long time. But the idea is that you put, when you talk about like probabilities, you want to understand, if I use the north path or the south path, would I end up with a higher probability of getting an entanglement? Would I have the right support from the underlying hardware that I can do the purification that I want, etc.? So, like I said, it's been sitting idle for a while, but it might be somewhere that you might look at from the point of view of enhancing it, putting in more properties of links and of nodes, so that you can, across a network, choose, this is the path I want to take, this is the entanglements I want to do, this is swapping I want to do, and this is purification I want to do. So I
Yeah,
can
thanks for that.
drop. Yeah,
Yeah,
I can
I'd
drop.
love to read it if you can share it. Yeah.
Yeah, I'll drop it in the chat
Great.
with that. Yeah.
Kiriti,
Great,
please
thank you.
drop it. Please drop that both in the chat and on the QIRG mailing list. It may have been mentioned before, but it's probably dropped off people's radar. It would be great to have it discussed on the list again.
Sure. Yeah, I'll do that.
Thanks.
Shota, go ahead.
Okay, Shota Nagayama speaking. So I would like to raise a question. So you said batch link, and actually that batch link doesn't generate entanglement anymore. So that's actually entanglement a bit distant and already created. Should we call that batch link?
Yeah, so
the-
sometimes this is called logical links as well. We've seen that in literature. So there are virtual links or logical links, but the idea is it is an already distributed entangled pair across two nodes that may be multi-hop.
Yeah, right. So but still, I have some doubt about that.
Okay. Yeah. I welcome your suggestion for the right terminology of what we can call those logical links or multi-hop links.
Yeah, thank you.
Thanks.
Thank you. Thanks, Michael. And
All right. Thanks all.
who's up next?
All right, up next will be Mone talking about timing regimes in quantum networks. Let me see if I can pull up her slides. Whoops, wrong one. Timing regimes in quantum networks. Here we go. You should have the clicker. Yeah, that'll work. That works. All right.
Hello, everyone. I'm a bachelor's student from Keio University. My name is Monet Tokuyama, and today I'll be talking on behalf of our group on a work in progress on timing regimes in quantum networks. Okay, so this is an example of a quantum network design. I'm not here to talk about the bigger picture of a quantum network architecture, but what we want to do here is our group has been thinking a lot on how we can divide or identify different layers in a quantum network. And we thought it is a good start to think of the different timing regimes of different components in a quantum network. And I want to show here on this slide is that they're just a lot of different components, and we have to think of each layer, like the hardware or the quantum side. Okay, so in a quantum network that distributes end-to-end entanglement, there are a number of tasks with demands on time and precision or jitter. And some of these can only be achieved by using high-quality hardware, like high-quality detectors, or some are just pure software tasks. And detailed analysis or research on these timing regimes, we believe that will affect the core of design of quantum network nodes. So here's a list of the timing regime that we propose on our document. And we can actually group these up into 3 groups. So the first group would be the quantum optical path. This is where the quantum mechanics happen, quantum optics. So from when we emit the photons to when we detect them and collapse them back into classical. And the second grouping would be hardware, so like detectors or optical switches or what we use to change the measurement basis. And the third one will be software. So I believe a lot of people here are engineers, so we'll be focusing more on the first part, which is quantum optics, and go through the hardware and the software briefly. So to give everyone a bit of an introduction, I think what we use in quantum networks, we use photons to communicate or to entangle links with each other. And here, everyone might know what a photon is, but I often think people believe that photons are like a particle or either a wave. But in our team or our group, we often think of photons as a wave packet. So a single photon could be described as a wave packet, and we all know that light is an electromagnetic wave. So what we're describing here is this is the amplitude of the electric field of a single photon. And yeah, so this is what we consider a single photon, and this is what we call the wave packet. So to look in more to this, let's say one oscillation here is the wavelength and one oscillation is 1.5 micrometers. So this is like 1560 nanometers. And this is what we use in optical fibers. So for classical fiber, even for classical communication, we still use 1560 nanometers fibers, and we want to use like the dark fibers in the ground for quantum communication. So for our experimental team, we also work towards achieving the 15-16 nanometer wavelength. And yeah, that's just an example. But so the 1.5 micrometers can be converted into 200 terahertz in frequency. And that is for one oscillation, it will take about 5 times 10 to the power of minus 15 seconds, which is the range of femtoseconds. So it's very short. And when we outline this wave packet, we can say this, we call this the envelope, or so it's like the shape of the wave packet. And when we think of how we want to interfere the two photons to achieve entanglement swapping, which is how we link together two nodes in a quantum network, we have to think of how these interfere together. So we want to achieve the same frequencies or the same shape of these wave packets. So a bit more on the wave packets. So I talked about oscillation time could be like a femtosecond range, but it differs on the technology that we use to emit photons in a quantum experiment of how many oscillations we have in a single wave packet. So it could be tens to trillions times the wavelength, and that will correspond to the duration time of a wave packet to be picoseconds to microseconds long. And if we convert that into length, a single photon could be up to like kilometers, or it could just be like a micron in length. So talking a bit more on these wave packets, there are two examples here with the same wavelength but different envelopes. So thanks to Fourier and Heisenberg, we know that wave packets with short envelopes have high uncertainty in wavelength because there are just many more superpositions of the waves in one packet. And yeah, this is just the same picture that describes in a different way. Okay, so getting right back to the timing regimes, the first one is an interferometric stabilization. So entanglement distribution in quantum networks is what we want to do basically, and it's performed by an entanglement swapping. And entanglement swapping, what has to be satisfied for entanglement swapping is the two photons have to be indistinguishable when we interfere them at a beam splitter. And the properties that can determine how distinguishable the photons are could be polarization, spectral modes, and other stuff. So here we can see that the figure here is showing two different wave packets. So if the wave packets aren't identical, they won't interfere. They would destructively interfere, and we can't see entanglement swapping. So we want to achieve the same properties. We want the photons to be identical, and that is purely on quantum optics. So it's not so much that we can engineer them in like software, but we also what we want to do, another component that we have to do is we have to overlap the photons. So we don't want them to be distinguishable. We want them to be indistinguishable, where we also have to think of the timing of the photons. So if the photons don't overlap with each other, we can also distinguish one from one. So like one can come first and one can come second. That means they're not identical. They're not the same. So that is not good in the sense of entanglement swapping. And factors that can lead to wave packets to not overlap is photon emission time jitter, which is just pure physical stuff. We can't really fix it. And physical distance difference between each nose is something that we can fix. So to give more on insight on this, so the two photons have to arrive at this box, which is the beam splitter. And if they arrive at the same time, they'll give good visibility, which corresponds to good entanglement, basically, in a quantum network. And so these blue things are the wave packets I was talking about. And you can see here that they are the same distance apart from the beam splitter, which they will probably interfere at the same time, because the speed of light is constant. So for a bad overlap, on the other hand, we can see here that the distance between the two wave packets are pretty far apart. And this case, they won't interfere with each other. And this will give poor visibility, which will not give us entanglement. So one thing that we can do to fix this in the practical sense is we can use an optical delay line. It's a device that has two mirrors inside of a box, and you can just like adjust the mirrors with like signals. We can connect it to a Raspberry and just like move a bit to the left or right. And this is actually what I work on more of the time, but things we have to consider when we're using this hardware is the time to calculate the delay needed for it seeing interference at the beam splitter. And we also have to calculate the time necessary to talk to the optical delay line, and also the time to set and reset the optical delay line for the future use. Okay, so moving on to the hardware part, I'm just going to go through these latter parts quickly, but detector timing windows are our third aspect in the timing regimes. And for an ideal single photon detector, we often call SPD, it will generate an electrical signal after absorbing a photon and only after absorbing a photon. But that's just the ideal case. In the real world, what's going to happen is we're going to have timing jitter or dark count rates, and that will affect the overall rate in entanglement distribution in a quantum network. So, and that's kind of on the hardware side, so there's not really much we can do, but we also have to take in account of the timing that, or the reduce in the efficiency in the network. And when we design the quantum network, we have to think of these parts. And another thing that we can help or fix in this sense is the recovery time. So once one photon is absorbed in a single photon detector and it generates an electrical signal, we have a time to wait for the next photon to be absorbed. So we can't just like send, we have to think of the intervals between two wave packets. So that's also one thing we have to consider during designing a quantum network. Okay, so talking about measurement basis selection, we need to monitor the quality of entanglement in a quantum network. And for instance, let's say we have like 1,000 bell pairs and we can use like 800 of them for applications, but we want to monitor the rest to see if the entanglement is actually efficient. And how we do that is we perform a thing called tomography, but we perform measurements on photons in multiple bases to see what the rate is. And to do that, we have to change the measurement basis. So how we do that, this is also related to hardware. We use wave plates, which is an optical component, but that is connected to like a motor. And we send signals to that motor to rotate the wave plate so we can measure in different bases, basically. And shifting that wave plate obviously does take time. So we have to also take into account the timing of shifting the wave plates. And optical switch control, I believe a lot of people here know what a switch is. So basically it is switching where the photons go, as like in any kind of network. But what we have to consider here is not just the time of how long it takes to switch from one path to another, but we also have to take into account of the interval time, the time again of when the photons, how much time they are between two wave packets. So think of a train, the photon wave packet as a train, and like when you want to switch the tracks, you can't just switch midway through the train or it's going to break. So something like that. Sorry. Okay, so from this part, it's going to be more on software, and this part is a lot on work in progress. The document is not completed yet, so I'm just going to go through the brief idea. So pre-configured event-driven tasks could be, so when something goes wrong in the networks, it's like a backup that the software can help you, but sometimes it might not work, and we're not quite sure on this part yet, so we're still under investigation. And for G, urgent but not synchronizing critical tasks, this doesn't necessarily mess with entanglement in the whole quantum network, but it is more something on the software side. So software does also take time, and it's here to make sure that the software we need, which is a big part of the network, that works properly. So moving on to the next software is host side application level tasks. So we do want to run applications on a quantum network, and the application that uses the service of our quantum network will pass through these several phases, and we can categorize these phases into initiation tasks and processing tasks and cleanup tasks. And each component will take a fair amount of time. So some components could be instantaneous, but others will have to wait for like the quantum parts of the network, and we still don't have enough resources or the quantum experiments set up yet to monitor all of these, but we have to think of these when we're actually designing a network. And last but not least, for the background tasks, the quantum parts in a quantum network can be scheduled to run during the low periods of traffic in a network. Since once we run the quantum applications or the quantum parts of the network, we have strict timing restrictions for the quantum to work. And the supporting classical calculations can happen in the time that we're not working too much on the quantum side. It can run in the back. So it doesn't directly affect like the quantum side timing, but we have to take into account when this fits in or when is the low traffic to run these background tasks. Like that could be link monitoring of the quantum particles or routing and other components. Okay, so this is still a work in progress, and the timing regime in quantum network document, actually the real one has like a lot of equations in it. So we're still not sure which venue we want to publish it at yet, but it will be available to the public very soon. And to give an overview or recap or summary of how much time actually it might take or the range of timing, just to give you an idea, this is not a sealed deal at all. We're still under research. We still need to do experiments to actually know the timing of how much a quantum part could take. But these are the parts we have to consider, and this is a brief idea of how much time each component would take. And some of these tasks in color-coded, some of these have to be synchronized with each other, but others are not necessarily that case. But yeah, that's pretty much it. Thank you for listening, and arigatou gozaimasu.
Yeah, thanks. Wow. I'm still stuck on
Way
kilometers long
Yeah.
photons. That's fabulous. Any questions, comments? We do have several minutes.
Hi, Chris Anasio. So it seems to me that this kind of work lends itself to like a limit study where you can kind of understand what parts of the system are physically limited. So like, let's say you have an ideal fiber and therefore you know your loss is going to be in the fiber. And so then you can look at all the other parts of the system what's the bottleneck? And you can keep doing that across all the different components of the system. It gives you the engineering guide of this is the part that we can get the most gain on today and move through it. Is that like the end goal of this kind of work?
From what I know from this work, I believe that we want to identify how we can actually structure like the layers, different layers. So it's not necessarily the end goal, but it is, in my sense, a start, because after we have an idea of how we can structure the network, then when we actually have more technology or like better components that suit our network, we can probably work from that. Or my professor can also answer to that.
Yeah, so Monet presented the work, but 3 of the 4 other people who are working on this document are here in the room, including me. So I guess it's okay for us to actually contribute to the answers here. The part of what we're trying to do with this is to define the constraints that will help us define layering in the system as we're doing it. And so we can define what responsibilities, what parts of the system are the responsibilities of the quantum optical engineers, the classical optical engineers, the classical hardware engineers, right? And so a lot of that's what we're trying to achieve. But as we're developing the document, we're also we're learning how to pick sort of a useful set of terminology. And so some of these things are constraints that are imposed by the underlying physics. Some of them are constraints based on particular implementations. And then at the other end, there are requirements that are imposed by what the system has to do and actually to do something useful. So those would be sort of business level requirements. And the document as in process probably needs quite a bit of cleanup on regularizing that set of vocabulary. So if you have guidelines or suggestions for what kinds of terms we ought to use, we'd be interested in those as soon as we have something that people can look at.
That makes sense, although I'm not a quantum network person per se.
Thank you.
Diego?
Yeah, well, was trying at the same time to take the notes of what Chris was asking, and etc. So it's no. One of the things that you said, Rod, at the end is about this need of a terminology that is well aligned, and from this analysis we can derive this. Because looking, you were mentioning routing,
Yeah.
and I was wondering whether when talking about this routing, you were mentioning the same thing that Michael was introducing before. It's the same kind of process or not, or we are talking about the path computation, or is the implication of having it distributed or centralized? I don't know. This is something that you are trying to identify, or when you say something like routing, or I don't know, especially when we're talking about the software tasks.
For the software tasks, most of them are like really, really still under investigation. I just kind of like push them together so I can present today. But we do want to identify more clearly, but still we are at the step of like, we still don't know how the software overall can work with like the quantum optics part. And especially, so we do want to like make it more precise, eventually the namings or the terminologies, but right now we're still just not at that step, is what I understand.
And the second reflection was about these
Yes.
measurements.
Yes.
This could be somehow, I mean, whatever the measurements, whatever the time regime, do you think that this could become some kind of mechanism to assess the quality, the metrics of a particular connection? So in order to make a path computation and evaluating it. So is this one of the goals? Because that would be extremely interesting.
Yeah, I do believe that is one of the goals. It is like at a research step to think of what we can do with what we have. So we do want to identify like the problems and make them into a system eventually. But yeah, in the document, we just don't talk about that too much right now. I think it's not a complete document yet at all. So we will be thinking of that. Do you have anything to add on, Redson? Yes.
Okay.
Thank you. Okay.
Okay, thank you so
Thank
much.
you.
Wait a minute, do we have anybody else?
Somebody, oh wait, I guess it's probably Diego. Oh no, yeah, Michael wants to ask a question. Probably.
Yeah,
okay.
I was just going to address the latter half of Diego's question. So I think something like this would be very helpful from a routing perspective to understand, how long do we have? How long does the SDN controller have to actually do these path computation decisions, right? So the timing regimes will really inform not only the architecture of the network, but the latency requirements where all of these path computation and scheduling optimizations can be done.
Yes. Thank you very much.
All right,
Diego himself.
great. Thank you so much. Yep.
Diego Lopez.
Yep. And Diego Lopez is up next, and go ahead.
That's right. I forgot. Diego's actually our note taker. I forgot we need somebody to take notes while he's doing that. Somebody want to jump in? All right, good. We got a volunteer to take notes here while he's doing it. Hopefully this clicker works. Test that. And we're doing fine on time. So it's 58 after now. I will stop you no later than 15 after because we've still got one more presentation.
Okay.
So you got plenty. You got plenty of time.
I will try to be brief anyway, just to note if we had time to. It's like you were mentioning when you have the class, a big class with few people. Right now is that if you you close the class 10 minutes before, people really feel grateful, don't they? Okay, so this is about update of work that we initiated or that we introduced in the previous IETF meeting in Prague, in which what we're trying to do is to propose an architecture, a framework. It's not that we are trying to provide the architecture of the future quantum internet, but it's provide a framework that help us in identifying how the different elements in a quantum internet, or better, in a internet with quantum capabilities should require, how the interactions of the different elements could be, and how we can support convergence for the future. And this is something that is down in on the slides, but it's very important. And this is taken from one of the references that we have added to the document. This is about an exclusively quantum internet is neither feasible nor desirable. And this is something that is important because it's not about that we're talking about a separate quantum internet that is somehow not aware of the classical internet. Is something that at the end, it would be desirable that what we have is something that is a wide network that has some quantum capabilities and allows us to use those quantum capabilities that are required, or interact with the network in a way that is classical, as we are classical beings. So far. So the idea, and this is taken as well from other the reference is about keeping universality. It's a general network able to accommodate any application. It's transparent, can share, and this is essential if we're talking about making this sustainable and or even feasible in the future. It's able to share physical media with classical networks, and is scalable. It's not about connecting 2, 3, 4 nodes all over the world. And it's not intended to be, this proposal is intended to be a set of protocols or interfaces or definitions in detail per se, but a way to describe and analyze the different proposals. And while Michael and Monet were making their presentations, I was taking my notes about how we could try to accommodate what they were presenting in the framework proposal. This is something that I will get back. I have as well a couple of students, not as many as Rod, and we'll try to make them work in the coming months on this. The second reminder is that, well, we try to, I mean, it's in the draft as well, to look about properties that we believe would be required for these frameworks about supporting agility. So it's possible to incorporate different technologies. This is very much related if you are following the QKD, PQC stuff about the crypto agility that would allow us to mix and match different techniques. Sustainability, and when talking about sustainability, I have not found a better term for something that would work, would incorporate different technologies and economical. So it's can be fully integrated. It's not only about energy consumption. It goes way beyond that. And something that for some discussions, I decided to use pliability. It's how you can adapt it with common best practices. We have been, for the last 50 or even more years, working in operating networks at scale and properly, and is how we can adapt or how we can incorporate those mechanisms into the network. So, and apply something that is important is applying the operational experience that right now in some environments we are deploying the first quantum-based communications infrastructure that are focused on QKD. And for that, what we propose is to use an architecture that is RFC 8597, that is a generalization of SDN principles, basically. And the idea is to go that way. And well, we made this proposal, we introduced this in Prague, and from them, we have been addressing some received comments, restructuring the draft, because it apparently from the comments, it was not clear what we were proposing. We were not proposing to build something based on QKD, that we're proposing to leverage that experience and try to learn from that experience, but is more focused on what comes after QKD, is not stopping by QKD. Start some discussion on synthetic environments. I will go on this later on, so we can learn before the quantum internet exists. And well, there are a few things to deal with. One is about the idea whether we should talk about quantum forwarding or something different. I have noted that Michael was talking about about forwarding as well. So that's something that we have to sort out, to map what has been already proposed onto this as a touchstone to show what we're doing. And finally, security considerations for the moment are totally, well, it's there. We are concerned with security, but that's the only thing we say. The current structure right now tries to make clear that QKD is a starting point, that is very important that we interface with classical networks for sure, and introduces the class architecture as another starting point. We separate this. In the original draft was a little bit intermixed and was not clear. Right now there is a section say what we are starting from. Second, what we are proposing, that is a new class-inspired architecture for quantum networks, and provides a set of principles about the different elements and why we are talking about those elements, and start talking about the synthetic environments. And then, well, security considerations or whatever that comes up. For the synthetic environments, the idea is that, well, taking into account that we don't have many of the devices we are thinking, or the devices are big lab-based devices that occupy several square meters and are difficult to combine and to run scale, etc. The idea is to start playing with things that are not necessarily, and there are tools there. We have started to use things like Squid or another quantum emulators and simulators, etc. And we're building something that probably people are talking about, that is a quantum network digital twin. I would not say it's a digital twin because we don't have the real thing to twin either. So I prefer to call it a quantum synthetic network environment, if you like. The idea we have started with this. these one of these students I was mentioning is working on these matters, and we are trying to validate the framework to identify which are the roles of strata and planes, and start playing with the interfaces, taking into account that one of the strata is purely classical, is pure connectivity, is physical connectivity, is how we establish a optical link between point A and B, classical one, and the interactions of these physical links and how that they are related to the quantum ones. And there is a third strata basically that is related to how I provide the service, how may the interface between the applications and the quantum quantum capable networks. And the idea is to assess this. We have started with first experiments. We will be presenting this. There are plans to present some of the results. Well, there is a paper already published. I will share with you the link, very much focused on QKD. And we are planning to present a couple of other papers in short time, showing the initial results. So if anyone is interested, we'll be more than happy to talk about that. And well, as I said, in the future, what we plan is for Vancouver and afterwards to keep working on these interfaces and protocols. There is a corpus of proposals already available, and the idea is to start investigating how they fit in what we are proposing and see how they can be part of the framework and how they can interact. And well, tell you, or hopefully in the future, many more of you tell you about what we are doing and which are the results, and keep the draft evolving to see whether, at least if it is not going to be finally published as an RFC, etc., but at least it is useful for a better understanding of how we can build something that, as I said at the beginning, goes somehow beyond the pure quantum internet and goes through or towards the availability of a global network with quantum capabilities. And with this, I have finished 21 seconds ahead of time. Thank you.
All right, thanks. Comments, questions? Anyone? Let's see. Scott. Go to one of the microphones that is very far away from where you chose to sit.
Okay, Scott Fleur, Cisco Systems. I just have a very quick question. What sort of security considerations are you looking at, or have you done that at all yet?
We are looking at, for example, since we are talking about the interaction of these three strata. If you allow me, these are the three strata. The one with interfaces with the applications, the one that is the physical classical network, and the one that has to deal with the quantum stuff, so to say. Physical considerations are among those three strata, how one can be subject to attack by an adversary taking control of the others, for example, and what happens inside, because that implies that there are control planes and application planes, etc. Basically, we're talking about this, more the traditional, if you like, ways of thinking about that. Okay. If you have in mind something about specific attacks to an entanglement, swapping or forwarding, etc., this is something that it's for further consideration.
Okay. Yes, I may want to talk to you later after the meeting. Thank you.
Okay. Perfect.
All right. I would encourage people to read the new draft if you have not. I have, but I don't actually have much in the way of comments right at the moment. If you have read the draft, please comment on the mailing list. I'm sure Diego is looking forward to the feedback on it. Anything else? Anybody else? Going once? Going twice? All right. Thank you, Diego. Up next is Shota. Let's see.
Okay, my name is Shota Nagayama. So I talk about a link level multiplexing mechanism from my group. Next slide, please. Okay. Summary. So multiplexing, we need a mechanism. So here we propose a multiplexing mechanism for by the link allocation update message and barrier message. So I explained the problem to solve as well. So let's think about the quantum entanglement swapping first. Okay, here is a three nodes and two link level entanglement here. And actually, entanglement is a quantum correlation between two qubits. So now in the repeater node, we can measure the quantum correlation between quantum correlation. So that is a true figure of the quantum entanglement swapping and quantum repeating. With that, so this is a measurement, the correlation measurement. So finally, we will find the quantum correlation between the end two end nodes. So for the sake, so we have proposed a protocol to set up connection. So first, we will find the path from the initiator to responder, and the packet goes through from the initiator to responder collects parameters of each links, like fidelity or throughput or loss or so anything. So with finding a path, and finally responder receives all the parameters, and it calculates a rule set optimized for the quantum networking. So the quantum networking itself is actually a complex distributed computation for quantum computing. So there is optimization, and the responder will distribute that rule sets to each link and nodes, and we will start the quantum communication. Oh yeah, it's like this. So gathering from parameters from initiator to responder and distribute. So let's see. Oh yeah, what is in the rule sets? So purification is a kind of the error handling for quantum networks, and weighting, entanglement swapping. So there are many things, and they have an order. So they are optimized, and the responder will distribute that to each node. Okay. So this case, okay. Now we have only one connection A, and the left center node thinks, okay, now let's contribute to connection A, the right one as well. Okay, and another connection is requested. So now they have to think about how to multiplex those connections. So yes, and this is a time division multiplexing. So first connection A, then connection B. Then what will happen here? So I said it's distributed computation. And in distributed computation, problems may happen. So inconsistent data. So here, inconsistent resource allocation. The center left node thinks, okay, let's contribute to connection B now. And the center right node thinks for connection A. So in this case, the end-to-end entanglement will be the diagonal one. So no one wants this entanglement. So this is problematic. So what will cause this problem? So missynchronized update of link usage. So okay, let's revisit the problem. So it's like this. The new rule set comes from node 4, go to node 3 and node 2. And okay, now the node 3 thinks, oh, I have new rule set. Now let's move to the new one. But still, the node 2 is contributing to the first one, connection A. So, oh, sorry. So my Mr. Qubit doesn't appear here, but still, just entanglement appears. So, so there will be a program here. What we need is actually the alignment of the timing to move to the next connection. So here, so we propose two types of messages, so link allocation update and barrier. So link allocation update messages negotiate the order of the connections to contribute. So that it has add functionality and delete functionality. So adding new rule sets or deleting all the finished rule sets for connection. And it negotiates the allocation order. The barrier message is here. So let's see. So the barrier message is coming with reply of the location resource allocation update, and it negotiates the timing to move to the next one, next message, next connection. So the purpose is makes both nodes move to next link allocation at the same time. The functionality is so aligning timing to next link allocation. Then what will negotiate? Yes, when to move to the next message. So what metric should we use? Time or maybe ID of generated entanglement? Actually, in this case, time, absolute time would be problematic because it depends on the precision of the synchronization protocol, clock accuracy, and distance. So, but ID is managed by the system, so this is more reliable. So summary, so we propose a multi-expressing management protocol. So link allocation update and barrier. So functionality is adding new connection and deleting new all the user connections. And we have a new message to align the timing, so barrier message. So by those, so we can resolve the problem caused by the distributed computation, so inconsistent data, inconsistent resource allocation. Thank you.
All right, questions, comments? All right, Diego.
Yeah, please.
And Diego has apparently called the ambulance.
No, well, but since I'm going to ask, I will remember at least what I'm asking. So, no, it's about the because you are talking about this problem of the shared infrastructure. I'm curious, when we are talking about these messages are supposed to happen in a classical channel that is interconnecting both forwarders or repeaters or whatever, right?
Yeah, so those messages, these are in a classical channel. So this is for management.
Exactly. So that assumes that there is a classical channel that is associated with the entanglement propagation. And second thing, that doesn't imply, but because you're not considering the resources inside the repeaters.
Yes, the resources inside repeaters. Yeah, so those qubits are inside repeaters, and so here, this protocol is for link level protocol, and now, so this link allocation updates for link between node 2 and node 3, and between node 3 and 4. So another link allocation update will run.
No, yeah, what I had in mind is the situations that happen right now in current routers, that you may have that the queues got full and then you start dropping packets.
Mm-hmm.
Will be a similar situation here, right? If the repeater has no resources for dealing with so many or the different.
Oh yeah, right. So in that case, the link allocation protocol, or maybe the responder has to think about, okay, now it's too much. So let's reject this request.
And finally, I guess that this is part as well of the.
Let me inject just one comment there. So this the link allocation update and barrier, this is mechanism, and policy will be different.
Okay.
And
Yep.
the policy mechanism will be a separate mechanism. And so the dealing with congestion or competing requests or something like that, your call admission policy and things like that,
Mhm.
that would build on top of this. This is just the mechanism for
Yeah.
actually okaying and implementing those.
Yeah, yeah, right. So now here we just use exemplify the round robin algorithm, but so it's a different problem as well.
And a final reflection that would imply that Monet has another time interval to consider. Yeah.
Mhm. Okay.
Other questions, comments? Anyone? Going once? Going twice? Stopping slides.
Okay, thank
All
you.
right. Let's see. So that's all of the main agenda items for today. Thank you,
Oh,
Shota.
okay. No, sorry,
Wait.
I forgot to tell one thing. So our specification is open, so you can find on our GitHub webpage.
Maybe you should share the URL either in the chat or on the QIRG mailing list.
Oh, yeah, sure, I will.
Let's see. So we are done with the primary agenda. We have a few minutes for any other business. Anybody want to bring anything up? In particular, my co-chair has been very quiet so far. Wojtek, any comments, announcements?
No, not really for me. Just that talks were interesting and I enjoyed the session today. Guess there'll be a question on the mailing list. When will be the next meeting? I believe the next one's in North America, and only the next one after that is back in Europe.
Yeah, so Vancouver and Dublin are July and November, and Wojtek and I have not yet actually sat down and talked about when we actually want to do the next QIRG meeting. Wojtek, you want to meet in Vancouver, Dublin, or both?
No, North America is unlikely for me, but Dublin sounds pretty reasonable. And I like using the European meetings to also engage the Euro QCI folk, because they are developing a lot of protocol level research stuff and deployment experience that would be valuable to bring to the QIRG.
And it has absolutely nothing to do with the fact that it's a 2-hour plane flight for you instead of 12.
It does help.
Usually for me, the July meeting conflicts with the end of our semester, but this year it's actually scheduled reasonably, so I may actually be able to show up in Vancouver, but no commitments yet. But Dublin sounds pretty good to me. So likely the next face-to-face QIRG meeting likely will be Dublin. Pay attention on the mailing list. Any other comments? Anybody? Any final questions to any of the speakers or any other announcements or business? If not, we are done, and I will give you back your 7 minutes. Thank you all.
Thank you very much, Dr. Ron Valmeter. It was a great cheering.
Thanks. Glad to hear it.
We have 7 minutes. Is there anything that we can talk?